I don't know if. Buenos días. I don't know if I'm going to put this back in the right place. Mucho gusto. No sé si la cámara está bien, pero.
Me va a ayudar a seguir. Cuando hay esos partidos de fútbol, ¿tu hijo hincha por Colombia o Brasil? ¿Cuántos años tenía? 6. ¿Ya pueden encargar el ojo? No, ya no. Ahora pueden hacer dos curvas.
I wish I could put my computer here so I can see my notes, but it's okay. I'm just going to be looking here a lot, and that's all right, right?
Pero no hay forma, ¿no? No. Porque yo ahí.
It's okay. I can't move it. If I have no choice, I'll make it work.
Ya quieres saber.
Está bien. Ay, no, no, está bien. It's okay.
En el canal de YouTube ya está. ¿Así? Sí, señor. Yo quiero dar una indicación de en qué momento empezar. Pues, como ya está el febrero, pues pues agarra la. Ah, bueno, lo que pasa es que no quiero ir a hizo la presentación, todavía no tiene el imagen de la cámara.
Is it okay or no? Huh? What happened?
La cámara es no.
It's not working?
Sí, adelante.
¿Es mejor?
¿Cómo se ve tu Marina? ¿Mejor así?
Is the camera, is mejor?
¿Puedo presentar?
Porque voy a mover entre aquí y aquí. Ay, ay, ay.
No sé si me atreves. A lot of students in another class.
When does their class end?
En clases de computacionales artísticas. Primero, ofrecemos disculpas por los líos técnicos para la transmisión. Continuamos nuestro seminario de investigación del Departamento de Estadística. Tengo el placer de presentarles a la doctora Charin Messenger. Ella es PhD en Bioestadística de la Universidad de Michigan, actualmente profesora directora del Departamento de Ciencias de Salud Pública de la División de Bioestadística de la Universidad de Miami. La doctora Charin Messenger will speak English. The conference is conditional review for a pipeline control design.
Gracias.
Thank you very
Gracias.
much.
Y gracias a todos para invitarme a tu universidad. Voy a hablar inglés porque mi español no está bien. No puedo hablar ciencia en español, pero voy a hablar inglés y tratar de hablar muy despacio. Si necesita algo, por favor, avísame y voy a explicar. Okay. I will talk in this speed. Is this okay? All right. So this work is conditional rock curves for a paired case control design. And this is joint work that has been developed over the past few years with two of my students as they completed their PhDs. The first is Yalda Zarnagarnia, and the second is Feng Miao. Oh, I can use this. Okay, so I'm going to start by first giving you the motivation for where this work came from. So as you just heard, I'm a biostatistician at the University of Miami, and a lot of my work is in collaboration with other professors in the clinical department. And so this work came from a problem that was introduced to me from one of my collaborators in the field of diabetes. I'll start by reviewing rock curve construction. I'm sure you're familiar with what a rock curve is, but I'm still going to review. I'll talk about the specific paired case control design, which was the design of the study which gave rise to this work. We'll introduce the development of the conditional rock curve. We'll also talk a little bit about the optimal cut point to be able to differentiate. When you have diagnostic testing, you need a cut point in order to be able to make this useful clinically. So I'll talk about how we've modified existing optimal cut points in this setting for the specific design. I'll show you some simulation results and some analysis of data from the problem that gave rise to this work. Is my speech okay? Yep, okay. So diabetes mellitus. I'm not sure if everyone's familiar with diabetes. I've spent the last 20 years of my life working in the field of diabetes. It's an inherited susceptibility. So type 1 diabetes, many people don't realize this, but diabetes as a disease, we've heard of type 1, we've heard of type 2. And these are actually very different diseases. Type 1 diabetes usually involves some inherited susceptibility to getting the disease. It's a chronic health condition that in general affects how the body turns food into energy. In patients with type 1 diabetes, what happens is that the body does not make enough insulin. So it's thought to be an autoimmune process that gives rise to the development of type 1 diabetes, where the person's own body starts to attack the cells that make insulin. I think I should just leave that there. The risk of type 1 diabetes involves both genetic and non-genetic factors. And currently, islet autoantibodies are the markers to predict type 1 diabetes. There's a lot of work that's involved in looking for prognostic biomarkers to be able to predict the onset of type 1 diabetes. And in this study, we had a cohort of autoantibody positive patients and autoantibody negative family matched members. So we had a data set where in the data we had families where one patient was affected and one patient was not affected. Okay, and so we were looking to see if we could be able to differentiate based on based on status of microRNAs, which are the biomarkers that we used. So in this study, siblings were matched by family identification. They're expected to have correlated biomarkers because they're part of the same family. And so we were trying to see whether or not we could predict the healthy siblings if they are in progression to type 1 diabetes or not. So the goal of the study was to look at the association of serum microantibodies with islet immunity and disease progression in relatives at risk for type 1 diabetes. We investigated the hypothesis that serum levels of some microRNAs are associated with islet autoantibody or autoimmunity and progression to type 1 diabetes. We had 150 autoantibody positive and 150 autoantibody negative patients, and these were family matched siblings. So the important thing to note here is that we had a cohort of patients where of these 300 patients, there was pairs, 150 pairs, one of which was positive, one of which was negative. And this is a key thing which gave rise to this study. So we wanted to find a family-based diagnostic biomarker with a cut point. So microRNAs are regulators of gene expression and are considered to be novel biomarkers for many diseases. The hypothesis is that the serum levels of some microRNAs are associated with islet autoimmunity and or progression to type 1 diabetes. And so our goal was to identify the microRNAs that were potentially differentially expressed, comparing autoantibody positive and autoantibody negative siblings. And in our data, we had expression levels for 93 microRNAs. Again, we had 150 autobody positive and 150 autoantibody negative family matched siblings in this cohort. And so this is like a case control design where the cases and controls are matched by family identification. So the unique feature is that there's exactly one case and one control for each family. And then we had correlated biomarker expression levels. Our goals is to identify the biomarkers predictive of disease among healthy relatives. We wanted to identify family members at increased risk of disease development, and also to initiate treatment so that we can slow the progression of the disease. Unfortunately, in patients with type 1 diabetes, once the process has started, it can't be cured or stopped, but there are many, many treatments available that are still in trials, but that are hoping to slow the progression of the disease. And so what we did is there was a set of microRNAs that we identified in differential expression analysis. And we submitted this is how this work, what gave rise to this work. This was years ago. We submitted the paper for publication, and the reviewers came back and they said, could you construct a ROT curve? Because our audience likes to see ROT curves to help us understand the performance of the biomarker. Okay, so we did that and then realized, hang on a minute, these ROT curves are based on marginal distributions of the expression levels in the affected and non-affected groups, and they don't really take advantage of the correlated nature of the design. It makes sense that the biomarkers should do a better job at differentiating between groups because there's less noise. You have a design that specifically has an affected and an unaffected member. So we expect the performance of any biomarker to do better when you have a correlated design, and the ROT curves were not reflecting this. And so we expect more informative AUC estimates and better performance when biomarker expression levels are correlated. And the existing methods for ROT curve construction don't demonstrate this. And I'll show you this with simulation, but they're really just based on marginal distribution. So they essentially ignore the paired nature of the design, which is really an advantage of this design because you're able to isolate differences within members of the same family to really see a better signal among the different biomarker expression levels. Does that make sense? Okay. So Are you all familiar with ROC curves? I assume you are. I'm just going to review them quickly. So ROC curves are widely used in medical research to evaluate the accuracy of a diagnostic test, or for example, in this case, to evaluate the performance of a biomarker. So what a ROC curve is it's a plot of sensitivity, which is true positive rates, versus false positive rates, which is 1 minus specificity, over the range of plausible threshold values. And the overall performance of a diagnostic test is often evaluated by the area under the curve. So if a ROC curve is uninformative, we expect the area under the curve to just be 50%. And what I'll say this in a minute, but what the area under the curve translates to is the probability that a random case will have either a greater or less than, depending on the relationship, level of biomarker than a random control. And if the biomarker, whoops, I don't know what happened here, but I've just lost my connection. Okay, so is this where I was? This is where I was. So we expect that, okay, if there really is not, if the biomarker is not informative of disease, we expect the area of under the curve to just be at 0.5. And it can be interpreted as the probability that a random selected control has a lower test result than a randomly selected case if test results are higher for cases than controls. Okay, so more formally, if we have continuous biomarkers for disease and non-disease subjects from a case control study, we can define the true positive rate and the false positive rate this way, which is the probability that the test result is greater than or equal to some threshold value. And the false positive rate would be the probability that a control has a positive test result. So the test result being greater than some cutoff is what's considered to be positive or negative test results. And then we can define survivorship functions for the disease and non-disease subjects this way, where these are just standard survivorship functions for the disease and non-disease subjects. So the ROC curve can be defined as essentially mapping the survivorship function to of the disease subjects to the inverse survivorship function to the control subjects. And this all happens over the range of false positive rates, varying from 0 to 1. So T here is a specific false positive rate varying from 0 to 1 as the threshold varies from negative infinity to plus infinity. Okay, so in order to talk about ROC curves, we need to talk a little bit about odds ratios, which this group is probably familiar with. So odds ratios can be defined in terms of sensitivity and specificity for a biomarker-based test. So the odds ratio is formally defined in terms of sensitivity and specificity this way. You can also think about this in terms of false positive and true positive rates. This is a summary measure of association that can explain the accuracy of a biomarker for classifying subjects. And it depends on the units of measurements. Odds ratios are just an index of association. They're no more informative than that. And so ROC curves can be constructed using a logistic regression model, as you are probably familiar with, where we have predicted probabilities of disease that are derived from the logistic regression model. However, these are affected by sampling probabilities. So as you may or may not recall from training or times where you first studied logistic regression, the predicted probabilities, which are the probability of disease, cannot be estimated accurately by certain designs. If you have a case control design, it is affected by the sampling probability. The odds ratio, which is the measure of association, is not affected by the design, but the predicted probabilities are. And so using predicted probabilities from a logistic model under a case control design to construct ROC curves is only appropriate under the condition that the sampling probability is independent from the biomarker level. And this is an important thing to pay attention to when using this type of a design and using ROC curves. So this is an example of what I mean by this, and this is in simulated data, where we have a cohort of 10,000 case control data, where we have 1,000 cases and 1,000 controls. We have 500 simulations. And so what you see here in these lines are what the ROC curves would look like under some different scenarios. And so the thing to pay attention to is that the blue line, the red line is the cohort study. The green line is the case control study without dependence between sampling. But the third line, this blue one, is from a case control study when we have dependence between the sampling probability and the biomarker level. And when that's the case, these curves will have some bias related to that. So we have to make sure that we don't have dependence. Some review of different ways to construct parametric ROC curves. So in a parametric ROC curve, we assume that the diagnostic text follows some kind of a known distribution. And then we can model the ROC curve parametrically using a length function and basis function. And then we estimate unknown parameters using standard likelihood-based methods. For example, if we assume that the biomarkers are normally distributed, then we can express what the ROC curve would look like based on the distribution function of a normal distribution. And then here are parameters to estimate would be these betas, and we have a link function here which is related to the normal distribution. And you can see these parameters are related to the true differences of the means of the biomarker expression levels in the groups and the variability of the biomarker expression levels in the groups. There are non-parametric methods of estimating ROC curves, and these are mainly empirical methods. These are distribution-free regarding the diagnostic test results. And here, true positive rates and false positive rates are usually estimated using the empirical cumulative distribution functions, conditional on disease status, which essentially just counts for all possible thresholds, the number of true positives and false positives. And then there are standard ways of estimating the AUC. An interesting note is that in this situation, the AUC, or the likelihood-based methods of the AUC, is equivalent to the Wilcoxon-Mann-Whitney test statistic. And I didn't put the reference here, but I can provide it if you're interested. But this is something that's been established. In 2000, Pepe introduced a semi-parametric approach of the ROC curve estimation using generalized linear models. And so this is nice because it provides an interpretation for each point of the ROC curve as a conditional probability that the test result for a randomly selected disease subject is greater than for a randomly selected non-disease subject, given the survival distribution of the non-disease subjects. So this assumes that test results from cases and controls are independent from one another, which is not the situation that we had in our design, and that controls are not matched to cases. The inference for the ROC curve is based on comparing all possible pairs of diseased and non-diseased observations. I'm going to talk a little bit about clustered data to get us into the segue of where this is going to go. So in clustered data, we have repeated measures. So we have multiple diagnostic tests on the same subjects, and there's been work in ROC curve estimation under designs arising or giving rise to clustered data. This measures the expression level according to each of two biomarkers on the same group of subjects. So you can imagine this might be something of interest if we have two potential biomarkers that we're considering and we want to see how they perform with respect to each other. And if that is the case, then we would have to have methods to compare the ROC curves that take into account the inherent relationship between these curves. In these designs, units are often nested within clusters and are correlated through some shared biological characteristics. And we can think of the data set that I described as an example of clustered data because they're shared by family characteristics with clusters of exactly 2. So, for example, data measured from the left and right eye of the same patient, or what I just described, familial type 1 diabetes, where we have sibling pairs where one member is affected and the other is not. So in our pair design, we have units that are nested within families and are correlated through some shared biological characteristics. They share some genetic material, they share some environmental factors. This helps us to eliminate potential confounding. And, familial matching can lead to bias in the associations of interest if the nature of the design is ignored, as I showed you in the previous slide. So for clustered data, there are approaches to ROC curve estimation that deal with this. For example, in 1997, Nancy Obashevsky produced an estimation of the variance of an AUC for a ROC curve generated under clustered data. So it essentially just adjusts the ROC curve's variability to take into account the correlation between measures taken within the same cluster. And she proposed a method for estimation and testing of differences in AUCs between two correlated ROC curves. So this would be the case where we have two potential biomarkers under investigation for detection of disease, but we have them measured on the same patients. So they're going to be related. So you can think about this as being clusters of biomarkers. The benefits here is that these methods estimate the variability and tests of significance in a correct way so that they do account for the correlation within cluster. There is efficiency gains in tests of significance because the variance estimation, we take out the correlation or the covariability in our estimates of variance. And there's no requirements in the method she proposed in assumptions about the intercluster correlation structure in the data. But the drawback in terms of our utility for these methods for the goal that we have or the project that we had in hand is that the estimation of the ROC curves and corresponding AUCs are marginal. They're unaffected by the clustered nature of the design. There's also semi-parametric approaches that have been available for quite some time for clustered data. For example, in Liu and Wu's 2003 paper, they proposed a model-based approach under a repeated measures design for ROC construction and calculation of AUC. In this paper, the idea was that you would have multiple observations on the same subject over time or different conditions. There might be some fixed effects, maybe gender and age, usually used for matching in a case control design. And then, or maybe there could be individual random effects that change over time. This was introduced using a random effect model or a GLIM model, and the model's based predicted probability of disease would be then used as a biomarker to calculate AUC. So this works except from many cluster designs, except not for a paired case control design where we have one case and one control in every pair. So what we need, so the issue is that these methods use conditional likelihoods to get unbiased estimates of model parameters in the matched pair design, and these do not yield predicted probabilities. So you may recall back in your training or whenever the last time whenever you first started to talk about conditional likelihoods or conditional logistic regression, where you have a positive and a negative, and you want to get an understanding of an odds ratio between some marker or some predictor and success or failure, you can get an accurate or an unbiased estimate of that odds ratio. But what you cannot do is use the predicted probabilities, because these are the conditional likelihood methods will be biased for the actual probability of disease. And this is a direct result of case control studies where the sampling probabilities are influenced by disease status. So let's come back to our motivational data and our paired family data. We have a case control design where cases and controls are matched by family identification. We have correlated biomarker expression levels, and we would like to construct a ROC curve that illustrates a biomarker's ability to separate cases and controls and taking advantage of the correlated nature of the design. Why else would we go through the trouble of having a design where we're looking to recruit only families that meet this criteria, because we want to be able to use the fact that the family members are related to help us see better what the differences are between them in terms of the biomarker levels. And so since, siblings share genetic factors and many environmental factors, this should really help afford more efficiency in being able to see relationships between biomarkers and disease. So we expect more informative AUC estimates and better performance of biomarkers when we have correlated biomarker expression levels or between cases and controls, which are related to each other. Existing methods that I've described and many others account for correlation in estimating the variability of the ROC curves, but the ROC curve itself is still based on the marginal distribution. So we want to do better. Thus, the introduction of conditional ROC curves. So conditional ROC curves are the new approach that we've developed to estimate ROC curves under these types of designs when we have correlated biomarker data, specifically from a paired case control design. Because as I've said, there's many applications in clinical literature or in biomedical applications where you have paired design by nature. You have 2 eyes, you've got for one, you have 2 ears for another. And in many disease processes, these things are in some way affected by the latent shared characteristics just because you're related. And in diabetes research or in type 1 diabetes research, it's a really informative design when you can get patients from the same family where one is affected and one is not. And we try to especially twins, but that's not always the case. Okay, so points on the conditional ROC curve reflect the conditional distributions for biomarker expression among disease subjects, given the expression level among non-disease subjects. So basically, we're conditioning on the expression level of the healthy subject to understand the conditional distribution for the disease subjects. So we can interpret the conditional ROC curve as the conditional probability that expression level is higher for a disease pair member compared to a non-disease pair member, and we're conditioning on the expression level for the non-disease pair member. So instead of thinking about it as a probability that a disease pair member will have a higher biomarker expression level than a randomly sampled control, this is conditional on that specific control. And so information about the non-disease pair member may be informative as to the distribution of the disease pair member's expression levels. We want to, if you think about a clinical application and if we're using biomarkers, we want to make sure that we're treating subjects appropriately, and knowledge about the non-disease family members will help us understand at what point should we worry about the biomarker levels of the ones that might be at risk. And so that's what we're dealing with. So in conditional ROC curves, let's define just some notation. We have the expression levels for the disease pair member, Y. We're going to let X be the expression level for the non-disease pair member. We're going to let R represent the correlation between X and Y. We've got the empirical survivor function for X. And then here is what's different. We have the conditional survivor function for Y given X. And so just like before, we had an expression for a ROC curve, which mapped the survivorship function for the disease pair members to the inverse survivorship function for the controls. We're doing the same thing here, except what we're mapping is the conditional survivorship function. And so doing this provides us a way to estimate what we call, or to express what we call, the conditional survivorship function. The key here is that this is based on a conditional distribution, which takes into account the relationship between Y and X. So before, everything was based on marginal. So we have a theorem that is proven in the published paper in Statistical Methods of Medical Research in 2021. But the theorem is that if Y and X are independent random variables, then the area under the ROC curve, or the conditional ROC curve, estimates the probability that Y is greater than X, but using the joint distribution between X and Y. So you see where that's different, because this directly uses the joint distribution, which takes into account the relationship between these variables. And so, assuming the test results are dependent from a family match case control design, the estimation of the conditional AUC from CROC can be shown to be equivalent to the non-parametric sign test statistic. And both of these theorems are proven in the paper. You're welcome to download it from PubMed, or I can give it to you. But this was an interesting finding. And so how do we estimate the conditional ROC curve? We're still working on other ways to do it, but what we've got so far is that, well, if we define an indicator variable, let's call it UI, which indicates whether or not within pair, the diseased pair member has a greater value for the biomarker level than the non-diseased pair member. We would have this for each pair, where n represents the number of pairs. So in some of the methods that I talked to you about before, this was done using randomly sampled or all possible combinations of disease and non-disease subjects. Here we're isolating it to the specific pair. Then we can fit a generalized linear model with the appropriate link function to these binary outcomes using the X values, the actual biomarker value for the non-disease pair member as a predictor. And so by doing this, we can end up with a conditional ROC curves where we plot the predicted probabilities versus the survivorship functions for X, which is the non-disease pair member. I'm not going to go into a lot of the weeds of the estimation, but this is really just estimation using maximum likelihood-based methods under generalized linear models. So if we assume the CROC curve is modeled as follows, using a link function, basis function, and unknown parameters in much the same way as the methods based on marginal distributions, we can use generalized linear models to estimate the parameters of this model. And again, these U's are just random variables from a Bernoulli distribution satisfying the properties of a generalized linear models. And we use estimating equations to be able to solve or to be able to get estimates of the parameters, which I'm not going to go into here, but if you would like to see them, they're all published in the papers that we've published. So for example, if we have a binormal case where Y and X are multivariate normal, then we can express the CROC this way using a multivariate normal distribution, and then beta 1 and beta 2 are estimated coefficients from that model. Okay, so we might want to incorporate covariate information just like in the marginal methods. So if we assume we have a set of covariates for diseased and non-diseased subjects at any given family, at any given pair, we can now express this conditional ROC curve where we condition on survivorship functions that depend on covariate levels. So here we would have the conditional distribution that the disease pair member has a greater biomarker value than the control member, and we're going to be conditioning on the value of the survivorship function corresponding to the control member, or where is their test value corresponding to their specific covariates, and we would condition on both covariate levels for both pair members. And here we can model the ROC curve parametrically. We have covariates involved, so we can actually get estimates of the relationship with the covariates as well. And we have, again, used estimating equations for that. I see I'm missing some of my slide here. I don't think I can fix that now, but I'll have to fix it later. So we can show that we have asymptotic normality result for the AUC based on the asymptotically normal distribution of the Mann-Whitney test statistic. This is, oops, I didn't mean to do that. This is shown in Bamber in 1975. The limiting properties of this are all very well behaved. We are able to show that there's equivalence between the conditional AUC and the sign test, which I said before. We can estimate the parameters of this conditional AUC either using parametric estimators, as we talked about before, or empirically. There are many ways to do all of that, which are described in the paper. But the important note is that these methods do take into account that conditional relationship, and we can get closed form expressions for the AUCs, and we can come up with confidence intervals. This is just some of the, just for completion, just to show you some of the theory involved in estimating the variances using likelihood-based methods. I really don't want to go into this in too much detail, other than to point out the fact that these variances do take into account the covariability between the biomarkers, and thus end up having increased efficiency because these are subtracted off. So another theorem that's published in our paper is that if we have jointly distributed random variables, y and x, indicating test results for diseased and non-diseased subjects from a family-matched case control design, then the conditional AUC, based from the conditional ROC curve, will be greater than the standard AUC values when there is correlation between disease and non-disease biomarker expression levels. And this is exactly what we assumed would happen. And we were able to prove it in closed form. This is in the 2021 paper. And so this is one of my favorite slides, even though it's not really pretty. It's just black and white and lots of numbers. But what you can see here are simulation results for AUC estimates and their confidence intervals for the paired case control design, where there's exactly one pair and one control. And in these results, what I'm showing you is this is the confidence intervals, and these are the actual AUC estimates. This is in a paired case control design with a standard AUC, ignoring the correlated nature of the design. And so what you have here are fold changes. So this can be thought of as the effect size, or the differences in the true simulated nature of the relationship between the biomarkers between the two groups. And as we go down the rows, the biomarkers should be more informative, meaning that they're much, much greater. They're 3 times, the expression levels are 3 times greater in the cases and the controls, 1 to 3. And then as we go across the columns, we're increasing correlation. And so if the biomarker performs better under a correlated design, which we expect that it should, because there's less noise, then we would expect these numbers to get greater as we move across for a fixed fold change. And what we observe here is they don't. And this is because these AUC methods are only using the marginal distributions of the biomarkers. So imagine, they can have very little, the only difference between them could be really related to disease, but we wouldn't pick up on that if we're only using marginal distributions. And so here is simulation results of CAUC values, conditional AUC values, and corresponding confidence intervals for the same ROC curves based on, again, correlation going from 0 to 1, fold changes going from 0 to 3. And look, if we have a correlation, if we have a fold change of 1, we don't expect there to be any informative nature of the biomarker because the fold change is 1. It's the same in both groups. But if we have an informative biomarker, let's say we have, let's look at 2, let's say that we have a biomarker on average being expressed twice as much, twice as high in the cases and controls, then as correlation increases, the ability of the biomarker to differentiate using the CROC approach increases. So this allows us to exploit the nature of the design. So these are the pictures from the simulated ROC curves and corresponding AUCs for the different scenarios. So here's the black line is if we have correlation is 0 and the CAUC is 0.68. Then the red line, correlation is 0.4 and the CAUC is 0.73. The green line has increased correlation to 0.8, and then the blue line is correlation of 1. It should be very easy. If it's correlation of 1, it's a constant difference between the case and the control. So you can see the biomarker performance increasing. And that's what I wanted to be able to illustrate when asked to draw a ROC curve. I wanted to take advantage of the fact that we had this great design. So here we have the actual data set that we worked with. And so I'm sorry that these numbers are all jumbled in the way this came out. But these are some of the microRNAs differentially expressed in the autoantibody discordant sibling pairs. These are just the names of the microRNAs. But if you compare the CAUC and the AUC, again, I'm sorry they're so close together. But you can see that in all cases, the conditional AUC tend to be a little bit higher, but in the two with the arrows, there was a very big difference. And these are ones that are being investigated as potential biomarkers for development of type 1 diabetes. These are the corresponding ROC curves, where we have for two of those two that I just highlighted. These are the corresponding ROC curves using the red, which is the C ROC, and the blue, which is the original ROC, the marginal based ROC curve. How much more time do I have? I know we started late. I'm okay still, right? Just a few more minutes. Okay, so we've gone through the formulation of the CROC. I want to talk a little bit about another way to approach this problem, which again is what we use to develop cut points. So we're going to start with a binomial. Here we're going to talk about the paired binormal model, which is what we've dealt with, but we're going to approach it a little bit differently. So here we've got a binomial distribution. Whoops. We start with a bivariate normal distribution where X and Y denote the normalized biomarker levels for the healthy and diseased subjects. And the difference between the paired and unpaired design is that there's an extra parameter now, which is that correlation between the levels measured on the cases and measured levels on the controls. In the unpaired design, we wouldn't have this. We would only have the 4 parameters relating to the means and the variances in the 2 different groups. But in the matched case control design, we have the correlation. So now we're going to deal with an approach where we're looking at these parameters this way. And suppose that the mean expression level in the controls is less than in the cases. We can think about the conditional distribution. This is just more formally, specifically for a binormal design. We can express the conditional relationship of y given x and x given y. And for a multivariable, a binormal approach, we can express what these relationships are in terms of the means and the variances in closed form. And then if we let phi be the angle between the conditional mean of y given x and x given y, we can think about a relationship specifically allowing us to understand how x and y relate. I don't really want to get into the technicalities here, but the fact that this thing is not perpendicular is what helps us to understand, or what illustrates the fact that these are correlated with each other. Obviously, we would have orthogonality if the correlation was 0. And so what we can do, another way to approach this specific to the binormal approach, is to transform x and y given y conditional on x. And the details for this are published or will be published in a paper that we're about to submit now. But we're going to call these decorrelation transformations, where we're essentially taking y and x and we're going to transform them by subtracting off and standardizing by the variability of y given x. So we're taking off the conditional expectation of y given x. So this is the disease subject's biomarker level given the undiseased or the controls, and then standard by the variability. And what we've proven in the paper, and which is well known for decorrelation transformations like this, is that the correlation between the transformed variables is 0. 10 minutes. Okay, I'll be less than that, I think. So what we have here is 2 markers now. Z, what I'm going to say is x conditional on y given x, and z of y conditional on y given x. So again, these are both transformed by standard normalizing with respect to the conditional distribution of y given x. When we do that, we end up with a set of uncorrelated measures. Once we have that, every tool that is available using marginal distributions is available to us because these are uncorrelated. And so we can, again, if we define these parameters, which are based on the means of the 2 different groups and the variability of the groups, and we can express the bivariate normal relationship between zxyx and zyyx this way, where we have the variance, we have the means. The mean of the bottom is 0 because it's y, where we're subtracting off the conditional mean of y given x. But we have the mean of xyx, which is what really we're going to make use of. And then we have the correlation matrix, or the covariability of the two. So this bottom term is going to have a standard normal distribution. The top term will be a little more complicated. And given that, we can think about the parametric sensitivity and specificity conditional on X, and we can derive a conditional ROC curve. So in the conditional ROC curve, we end up with a vertical axis, which is the true positive rate. This is the cumulative density function of the transformed random variable at a specific cut point. This cut point is C. And in the horizontal axis, we have the true negative rate, and this is the cumulative density function, which is a function of alpha, beta, and the transformed random variable at a cut point C. So we end up with a function of a conditional ROC curve based on the cut point C. All this is a specific way. This is not different than what we had before, but is specific to a binormal design, bivariate normal outcomes. And so here, this is just mapping, again, it's coming up with a ROC curve by mapping the distribution functions, but now we have them transformed to be something that's independent. So it's important in practice to develop an optimal cut point. So usually when we have diagnostic, prognostic, and predictive biomarkers, they're either continuous or ordinal. We have cut points on these biomarkers, which allow us to separate subjects into groups. And so the correctness of classification is usually measured by two rates. One is the true positive rate, the other is the true negative rate, which is sensitivity and specificity. And what we want is a cut point that optimizes the process, including the ROC curve-based criteria. And so that's what we've developed next. So these are some criteria that have been used to being able to figure out what is an optimal cut point. I will tell you, as a biostatistician, I mean, it's come to me many, many times over 21 years where investigators have asked me, okay, well, tell me the cut point. What is the point that I can say this patient has the disease, this patient does not? That is not a simple answer. And really, I mean, there are many approaches to developing what's optimal. And this depends on really how do we regard mistakes in the failing to be able to detect a positive, or mistakes in falsely saying that a negative person is positive, right? So you have to figure out how you maximize the optimality based on what the value of those different mistakes are. There's a few different approaches that are in the literature. One of the more popular ones is something called the Uden index. And the Uden index really measures the Euclidean distance here between the ROC curve and the identity. And so this is a function of the sensitivity and the specificity. And it tends to be maximized when we have maximal true positive rates and true negative rates. And you can see it's a function of Euclidean distance. And so if we look at this graph right here, if we assume that biomarkers from both cases controls are normally distributed, we can use this parametric Uden index to help us figure out what an optimal cut point would be. So the shaded areas here are the sensitivity and specificity. So we have the specificity in blue and the sensitivity in green. And if we suppose that the expected value of the biomarker from the case group is larger than the control group, then the sensitivity, again, that green shaded region, you can see, which is to the right of the cut point, and then the blue shaded region is the specificity. And these can be expressed by the cumulative distribution function. And you can show that you end up with maximizing the sum of the sensitivity and specificity, which is the optimal cut point, at the point where these curves intersect. And so here's an example of that. The Uden index, again, is calculated this way, but you end up with the cut point that ends up being right at this level. And here is the corresponding specificity and sensitivity according to the ROC curve, both based on parametric. You can see the parametric and the empirical based ROC curves. This cut point here is based on the Uden index, and it maximizes the criteria for the combination of true positive and true negative rates. So, okay, that's great. And it cut points map to a clinical decision, but what about in a matched case control pair design? How do we do this? Well, if we take advantage of the fact that we have independent distributions because we have a decorrelated transformation of X and Y, we can just directly apply what's been done in the literature in terms of optimality for cut points using the Uden index. And so here's an example of looking at the distributions before and after transformation. And you can see how here we have a sensitivity and a specificity before transformation of these values, but then we have a slight drop in specificity, but a big increase in sensitivity here. So we end up with a cut using, by decorrelating the variables, the outcomes for the disease and non-disease subjects, we're essentially able to more clearly delineate or find a cut point which maximizes the combination of sensitivity and specificity when summed together. I think I've already shown you this slide, so I don't really know why I think I've just doubled my slides. Yeah, we've already done these slides, right? So this is just a formal way of stating what the conditional, whoops, I apologize. So, okay, again, this is repeating the parametric approach to the conditional raw curves. So I have that written out here as we had before. And then from that and using the decorrelation transformations, we can come up with a cut point. Again, this is all, the details of this are all in the paper that we're publishing, but this gives you what the optimal cut point would be for the bivariate normal distribution under this framework. And so if we have b equal to 1, it can be expressed this way. If beta is not, beta is just the ratio of these variances. So it affects on the ratio, it's affected by the ratio of the variances for the two different conditional distributions. But if beta is not equal to 1, then that means there is a difference in variability and the cut point's a little bit more complicated, but this does map directly to the optimal cut point based on the Uden index. And so here's some simulation results where we can look directly at an example where we have correlation coefficients at 0.51. So it's moderately correlated. It's not ridiculously strong. And then after the decorrelation transformation, the correlation coefficient is 0. So these two figures illustrate how the probability density function curves change before and after the transformation when comparing the two groups. I mean, you can see that there's much more separation with the decorrelation transformation, when that separation is what makes it easier for us to be able to depict between the two groups based on biomarkers. And so you can also see how the ROT curves change both before and after the transformation. So the ROT curves here are a lot more flat, and you can see the AUCs. And then here they're more raised. I mean, you might argue that 0.63 and 0.69 isn't a huge difference, but it's 63% versus almost 70%. And really these are only correlated at around 0.5. So this would just be exacerbated as we go further. And then in the scatter plot by cut points, you can see more separation between the discordant pairs. So here we have much more separation. That when we do the transformation, we're able to differentiate between the groups a lot more clearly. Okay, so this is just the results using, again, the same biomarkers we worked with before. And now we're going to be using the ROT curves and the conditional ROT curves. And really, these are just sensitivity, specificity, Uden index, and a p-value that corresponds to the chi-square test of being able to see whether or not the groups are different. And so here in screening potential biomarkers, we have the pair of observation where we excluded all missing values. So anywhere where there were missing values, we excluded them. The cut points were optimized by the parametric Uden index, and the significant dependence between MIR412 and type 1 diabetes was not found from the literature. So this was a new finding based on these results. So the rest of these results where we found significant relationships, there were already mechanistic pathways that were understood and that makes sense for type 1 diabetes of why these might be different. This is a new one that was discovered, so this is being researched a little bit further now. The association between type 1 diabetes and all other biomarkers have been reported in the literature before. And then we have, I'm only showing you the biomarkers that ended up with p-values below 0.0001. There's plenty others. But you can see that the sensitivities and the specificities, generally, if the sum of the two is always greater under the conditional ROT curve, and which is depicted by the Uden index being increased. And so we end up with better performance under conditional approaches to these designs. And that's all I've got. So I did say thank you in Spanish. And that's it.
Gracias a la profesora Shari Messinger. Si hay alguna pregunta acá en el auditorio o a través de YouTube, nos pueden contar, por favor.
Okay.
I have one question.
Okay.
First of all, thank you for this is not my work area. My question is now, you are using parametric and non-parametric methods.
Mm-hmm.
Are there comparisons between the power of these approaches? You use parametric and non-parametric approaches.
Mm-hmm. Mm-hmm.
My question is, if you know some words comparing the power of these approaches.
There are. So in the papers that we published, I don't have them on the slide to show you, but in the papers that we have published, we have simulations using many different approaches. Empirical, which are non-parametric, the conditional ROT curves based on the parametric and semi-parametric approaches, as well as the marginal approaches, both parametric, semi-parametric, and non-parametric, all in big tables to show the differences. The better option is, as you would assume, if the parametric assumptions are met, you're always going to do better with parametric approaches. The problem is that we don't always know what are the true distributional properties of these biomarkers. And so for that reason, parametric approaches, as you know, can very well be biased if the distributional assumptions are not correct, right? So you do get efficiency gains if you use parametric approaches when you truly are simulating under the assumptions that those parametric approaches have, but it's a bias variance trade-off. In large sample, I prefer to use parametric approaches under the assumption of bivariate normality, because in large sample, we end up losing a lot of the bias. We don't, and we don't normally have very large samples, so we can't rely on large sample theory. Even though many of these do asymptotically become normally distributed, we don't normally have large enough samples. And then we also oftentimes, another complication of these biomarkers is there are limits of detection. And this creates problems in the distributional assumptions. So we end up using non-parametric approaches more often. Yep, it's a good question.
Have you found a lot of limitation for the test control in this case, because it's not disease, disease for biomarkers, while you experience in that study, the limitation of the study, or was easy for you to find the patients for the study?
So the patients for the study typically come from a study called TrialNet, which is a very large cohort study. I think that's been in existence for decades, which is specifically designed to recruit families where one sibling has diabetes and another one does not. And so there is, in many clinics and hospitals, at least in the United States, when a patient comes in who is newly diagnosed with diabetes, they will be asked, are there other children? Can we test them to see whether or not they have the autoantibodies which make them at increased risk? And then if the families consent, they enroll in this trial. And it's a giant cohort study that follows over time. So because we have access to that data, that's how we've been able to get the data that we have. In general, you know, the numbers are never going to be huge because it's, you know, it's especially when you deal with children, it's hard to recruit patients into these studies. But these are studies that aren't doing any experimentation. It's just following them over time. So many families tend to want to be involved in these studies because they know that that the physicians are watching their siblings to make sure that, you know, we're making sure that they're not progressing or they're not developing disease. Type 1 diabetes is a disease where it's very important to diagnose as quickly as you can because it can result in heart problems, in vision problems, in nerve problems. It's you know, I don't know if that answers your question. Does that answer? Yeah. Yeah. Right. And so that's why when we were working with this data, when I was working with this data, this is where the whole thing came from because we were able to find, so we developed methods of analysis very easily to look at, to determine differential expression between the cases and the controls and to accommodate the fact that there was, I mean, you can think about this as a random effects model, to think about the difference between cases and controls and then adjust for the fact that there's shared variability between members of the same family. We had a list, but then the question was, can you show us the biomarker performance? Give us a ROC curve. And I realized that these ROC curves are not demonstrating any benefit of the design. It's actually attenuating the relationship or shrinking the AUC. And so this is where it all came from, but we already had the data available to us. Yeah, you're welcome. Okay.
Muchas gracias.
Por nada. Thank you.
Siempre bienvenido.
Thank you.
Muchas gracias.
Oh, you're welcome. Thank you.